Hey, everybody, it's Russ Altman from the Future of Everything podcast. Well, the World Cup is here, and we're watching some amazing athletes on a global stage. And as we watch them, we might wonder, what is all that exercise doing to their body? That led us to think, hey, let's rerun an episode with Stanford biochemist Jonathan Long. Jonathan studies the chemistry of exercise. When you exercise, what chemicals are released by your body and why? His studies are finding some pretty cool things that may lead to new treatments for obesity and diabetes, and maybe, just maybe, an exercise pill. So as you're watching the athleticism on the pitch, you might want to re-listen to this episode about the future of exercise. This is Stanford Engineering's The Future of Everything, and I'm your host, Russ Altman. If you're enjoying the show, or if it's helped you in any way, please consider sharing it with friends, families, and colleagues. Personal recommendations are one of the best ways to spread the news about the show and the future of everything. Today, Professor Jonathan Long from Stanford University will tell us about metabolism, obesity, and exercise. He's an expert at the chemicals that get released by your body before and after exercise, and he's using that to understand ways that we can fight the obesity epidemic, the diabetes epidemic, and even someday have an exercise pill. It's the future of exercise. Before we get started, a reminder that if you're enjoying the show, please consider sharing it with friends, family, and colleagues. Personal recommendations are the best way to spread the news about everything. We all know that there's an epidemic of obesity in the United States and really increasingly worldwide. We also know that it's related to type 2 diabetes, and we all know that exercise is good for you and that diet and exercise is one way to lose weight, avoid diabetes, and feel good. And yet it's so hard. Moreover, we don't really fully understand in a specific way how exercise affects our physiology and leads to all these benefits. In fact, if exercise was a pill that you could just take, it would be very popular. We would have muscles, we would have less fat, we would feel great. But alas, we don't have those pills yet. But Professor Jonathan Long from Stanford University is a professor of pathology, and he's an expert at exercise, metabolism, obesity, and diabetes. He's going to tell us that there's more than you think understood about exercise, and he's going to tell us that there might be a future, not soon, where there is an exercise pill. So Jonathan, it seems like effective weight loss drugs have just exploded on the scene in the last couple of years. What happened?
Well, thanks for having me, Russ. I mean, it's really crazy what's been going on with Ozempic and semaglutide and all of the GLP-1 receptor agonists. The history of this whole class of medicine is really fascinating, starting from very, very classical endocrinology back in the 1980s, when it was discovered that, you could cleave these peptide hormones out and that they existed. And, it's really been a 40-year journey from that initial basic science to what we now know today as like a pretty safe and remarkably effective weight loss drug. Really over the last 10 years is when people started to really understand the therapeutic potential of these medicines. Because what happened was they got put into people initially for diabetes. And then when they put these drugs into people for diabetes, this was around 2010 or so, they started to see some modest weight loss. And that was interesting. And it was good that the folks at Novo and Lilly decided to pursue that further, because upon optimization now of those medicines, you just got bigger and bigger and bigger weight loss without any sort of untoward side effects. And so it's really been a remarkable journey, starting from basic science 40 years ago to really the last 10 years of pharma taking an initial signal in people and translating that into an incredible medicine.
I love that story, and thank you for that synopsis, because what it tells us is that even though in the public consciousness they just hit the market like in the last couple of years, the fact that this is basic science discovery and multiple decades of research is an important lesson really for everybody about patience and having faith that by understanding the basics, and this is what we're going to get into next, understanding the basics of how things work, you wind up with these kind of blockbuster discoveries. So now let's step back, and you're an expert in metabolism, metabolic diseases, the effects of exercise, especially on physiology. So tell me a little bit about how your lab approaches these questions.
Sure. So by background, I'm a chemist by training. But sort of unlike most chemists, I have a fundamental and very deep interest in metabolism and human physiology. And so that's sort of where the types of problems that we work on. But we approach these problems not from sort of a more medical view, but from a chemical view. And the way it works in chemistry is you always start with molecules, okay? And molecules are the key because molecules provide you clean handles to start to understand complex processes. And so when we start to think about exercise, which is a complicated state, involves many different things. I mean, some people can't even agree on what physical activity is. What we try to do is we try to find molecules associated with that state that are uniquely associated with that state, ideally, and then to use those molecules as very, very clean tools to access some subset of that state so that we can study it.
Great. Okay. So that's very clear as well. So this is super fun. And I'm exploding with ideas because exercise is something that's on everybody's mind. So the first basic question is, do you have to do these studies in humans, or I'm hoping mice, rats, other kinds of animals have very similar responses to physical exertion, or is that a dangerous thing to assume?
I think it cuts both ways. I think that there are examples of processes that are human specific, and I think there are examples of processes that are common to physical activity across all different types of organisms that move. So for example, in some of our work, we found an exercise-inducible metabolite that makes you stop eating. We think that this is the reason why, for example, after a very hard workout, you don't feel very hungry. And it turns out that this molecule, which is called LAC-Phe, is induced by...
I'm going to just pause because I want people to know. It's LAC-PHE.
Exactly.
Don't forget this molecule. Okay, keep going.
So this particular molecule, it turns out, is turned on after high-intensity exercise across basically any animal that moves. Okay, so we originally found it in mice. It turns out it's true in people. It turns out it's true in race horses that are racing. We've done other studies in the sled dogs that are running across the Iditarod. Basically, any animal that moves turns on this molecule. So that's an example of a molecule that's conserved across different types of physical activity. But there are also other types of examples of molecules that are human-specific or only in certain types of animals, too.
Great. So one of the things that I might imagine would be different for human is I know that when I'm getting ready to like go on a long bike ride or do a run, like I have to get psyched up for it. And I'm wondering, are we anywhere near understanding the process of like psychological preparation for exercise, which I might imagine would be different in human. That's why I'm asking it right here, is that I might imagine that mice are a little bit more ad hoc in their exercise, whereas I'm sitting around planning my whole weekend. So what do we know about that?
I think that's one of the most mysterious areas of exercise science, right? So the other way of sort of asking what you've asked about, for example, is if you look at marathon runners, okay, and you ask, why is it that they can't go faster? Because at the end of a race, it's not that their muscles are exhausted, right? Because they're still walking around. So there's some important psychological aspect of all of sports and activity that we don't really understand well. Now, what I can say is that there are starting to be emerging studies to try to find molecular and genetic underpinnings of, for example, motivation to exercise or preparation to exercise or pushing the limits of exhaustion. So, for example, there was a beautiful study that came out a few years ago that described how endocannabinoids, which are a class of lipid neurotransmitters, are involved in the motivation to exercise. And that's very interesting. And so, so people are starting to...
I just want to highlight, you just said the word cannabinoid as in some of the molecules related to marijuana. Is that correct?
Exactly. So, when you smoke marijuana, the reason that you have some of the pleasurable and also other psychoactive effects of that drug is because you have a receptor in your brain, the cannabinoid receptors. And it turns out that you have natural ligands, natural molecules that activate those receptors. And those are called the endocannabinoids. And so there's a paper talking about motivation exercise. And what they showed was that you have that the motivation exercise is determined by the natural rise of endocannabinoids in your body. And that's an important factor in what you were just describing in terms of getting yourself psyched up.
Fantastic. Okay, so let's go back to LAC-Phi because it was one of your big discoveries. It got a lot of press. People are excited about it. Tell us what it does. So I think the first thing you told us is that it is pretty universally present, I believe, at the end of exercise. And do we know, is it just telling us that exercise happened, or is it doing important signaling to the body that it should start, other things like building back the muscle or recovery, or what is it doing?
Right. So LAC-Phi is a molecule that's derived from lactate. Okay, so high lactate levels cause the production of LAC-Phi, and that's why it rises so dramatically after sprint exercise. And then what we found, it probably does many, many things, but the first thing that we found it does is it goes to the brain to suppress your food intake and suppress feeding and appetite. Okay, and so as I mentioned, we think that this is why, for example, you don't feel hungry after a very hard workout. Now, we've since learned that where this molecule is actually made is in your gut. So it turns out there are intestinal epithelial cells in your gut that make LAC-Phi, and so this represents sort of a gut-to-brain axis that's controlling feeding behaviors. But of course, the gut-to-brain axis controls many, many other things, including, for example, feelings related to anxiety and depression or happiness or different types of motivations or the behaviors.
We all have had a stomach ache when we're nervous about something that's about to happen, right? That's part of the same phenomenon.
Exactly. And so we are actively looking at other things that LAC-Phi might be doing related to the gut-brain axis. But one thing it does for sure is feeding, and probably many other things in the brain as well.
Okay, great. And presumably the lac part is from the lactate, and that's provided by the muscles that are producing, and it kind of goes to the gut. The gut creates this molecule. How long does the molecule last before it's like down to baseline levels?
In humans, it lasts a really long time. So if you, for example, have a person and you give them what's called a cardiopulmonary treadmill test. Okay, you basically put them on a treadmill and tell them to run until they want to stop. Okay, so they'll run for 10 minutes, be very exhausted. Lactate levels are through the roof. LAC-Phi levels are through the roof. And if you now look at 1 hour later, the lactate levels will have come back down to baseline, but LAC-Phi levels still remain high. If you check 6 hours later, it's still very high. Okay, and it only comes back down after 12 hours or 18 hours in people. And so it lasts a very, very long time after a single bout of acute exercise in people. And what's so interesting about that, by the way, is that what that means is this is, I think, part of our body's sensory system that can convert a very, very short stimulus, like a high intensity interval training session, into a very long and profound effect physiologically, right? Yes. This is part of the chemical logic by which that happens.
Yeah, that really is. That's very helpful because that does make sense. Because the question is, okay, I only did it for 10 minutes, and an hour later, I'm back on the couch watching The Simpsons. Why am I still getting benefit? And now you're beginning to understand that these molecules are hanging around. So what happens what's the difference between the response in a very well trained athlete and a weekend warrior or a couch potato?
That's a great question that we've just started to look at because we've only started to recently get access to those type of samples. And what I can tell you is that it all has to do with how they metabolize lactate. So in a very well-trained individual, they typically have develop very good systems for metabolizing and handling their lactate. What that means is in those individuals, actually the LAC-Phi doesn't go up as high. Whereas if you take an untrained individual who does not have those systems built in now after training to handle their lactate spikes through the roof, and their LAC-Phi also spikes through the roof. And so we think that there's a more pronounced effect of this whole pathway in untrained individuals versus trained individuals.
Fascinating. Okay, so I want to get to diabetes because you study exercise, but part of your motivation, if I understand it correctly, is trying to understand metabolic disease, and kind of the king or queen of metabolic diseases in many ways is type 2 diabetes. It's a scourge in our population. It's becoming a global problem. What are we learning about diabetes and the relationships to exercise and metabolic physiology, and maybe these molecules? You haven't mentioned whether LAC-Phi has anything to do with diabetes directly. So where are we in understanding that? And because we started out with the discussion of these drugs, many of which started out as diabetes drugs.
Exactly. So, you're absolutely right that, for example, diabetes and exercise and obesity all go hand in hand, right? And in fact, diabetes complications are one of the major problems associated with being obese. You can't control your blood sugar. You have diabetic retinopathy. You have all sorts of problems associated with uncontrolled blood sugar. Now, in right now where we are is it's very clear with the new drugs that are available, Ozempic and all the other GLP-1 receptor agonists, that as you start to control your body weight, that alone is sufficient to confer control over diabetes. Okay. And so now, instead of, for example, thinking about these as separate things, now more of the thinking is, how do we start to lower body weight safely and effectively? Because if we can do that alone, we start to resolve some of these obesity-associated problems, which include, for example, diabetes, include fatty liver disease and hepatosteatosis, which include dyslipidemia and cardiovascular complications. And so we've been mostly focused on the energy balance side of things. Now, you asked about lac-Phe and diabetes. So it turns out that if you give lac-Phe to obese animal models, what happens is they start to lose weight, and actually their diabetes resolves, okay? But we think that that's not necessarily a direct effect of lac-Phe on the glucose control systems, but is a secondary effect to the fact that the animals are now leaner and therefore metabolically healthier more generally.
Oh, I see. So, yeah, so there is this legitimate question of what's the mechanism of action by which lac-Phe it makes these changes. So, do you see, so I was going to ask you, and I think now is the time, do you see lac-Phe as being the core idea for a new weight loss drug? Or do you think we've already captured most of what it does with the existing drugs?
Well, I think that this is the core, but we have to put it in the right context, okay? And the analogy I would draw is what we talked about at the very beginning with the GLP-1 drugs. The first, I mean, we understand this now as a blockbuster weight loss medicine, but the first indications that it might be something were in the 1980s with academic experiments that were done at the NGH, okay? And now, 40 years later, we've translated that in a very, very successful way. What I think where we are with exercise science broadly and where we are in our current lab right now with lac-Phe is where we were with GLP-1 in the 1980s. We're just uncovering the fundamental basic sciences and basic understanding of the pathway so that we can set ourselves up over the next decades to try to think about what parts of this pathway might be therapeutically harnessable for the next generation of weight loss medicines or the next generation of anti-diabetic medicines. So I think that's where we are.
Yeah. So, and just to finish up this segment, let me ask you about, you were talking about diabetes and the direct and maybe indirect effects of lac-Phe. And that raises this larger question that I wanted to ask, which is, does it matter how a person loses weight? Or is the only point or the main point to lose the weight? So you can imagine that I could take drugs, I could exercise, I could stop eating, I could do all three of those. You and I have friends who are doing this kind of proactively for life extension reasons. Maybe we'll get into that later. From your understanding of the basic chemistry, does it matter?
So I'll give you a yes and a no answer. Okay.
Okay, good.
So the no answer is, if you are overweight or obese, it's always good to lose weight and come down to a normal, healthy weight, because the increased body weight alone puts you at risk of all these cardiometabolic complications. Okay. Yep. So that's the no part of the answer. But there is an important yes part of the answer, which is that as you start to lose weight, weight in our bodies can come from two places. It can come from either fat mass or lean mass, which is muscle tissue. Okay. And what you would like to do is you would like to lose fat, but preserve your lean muscle mass. And so what that means, for example, is that you would like to keep resistance training to keep your lean mass while you're, for example, reducing your caloric intake so you can lose the fat mass. Okay. And it's very, very difficult as someone loses weight to change the body composition. So it's very, very difficult to maintain the fat loss while keeping all your lean mass. But to the extent that you do want to do that, that would be the ideal situation. Okay. So to summarize and to answer your question, what you want to do is, if you're overweight, you want to lose weight. And ideally, you want to do it by losing fat mass without losing lean mass. But that's a very difficult thing to do. And it depends on sort of where you're starting from.
This is The Future of Everything. And I'm your host, Russ Altman. More with Jonathan Long next. Welcome back to The Future of Everything. I'm your host, Russ Altman, and I'm speaking with Professor Jonathan Long of Stanford University. In the last segment, Jonathan told us about this very exciting molecule, lac-Phe, that builds up after exercise, suppresses your appetite, and is involved in all the signals that tell your body that you just had a good exercise session. In the second segment, he's going to tell us about what's the possibility of a pill for exercise. Is exercise like a medicine? Why is everybody taking metformin, and how is this all going to play out in the years to come? So, Jonathan, I wanted to ask you about this idea that exercise is like a medicine. And I've heard people talk about this before, but it sounds like you're in a particularly good position to tell us if it really makes any sense.
Yeah, so I think this is one of the most interesting ideas that's been proposed and has been around for very long, right? Exercise is medicine, okay? And even you'll read about it in the Washington Post, you'll read about it in the New York Times, all over. And I think it's a very interesting comparison because nobody digs just one level down. People say exercise is like medicine because if you move, you start to lose some weight. This provides benefits for your body weight, for your blood pressure, for your cardiometabolic risk factors. All of that is true. But the next level down is, in what ways is exercise not like a medicine? And to answer that question, we have to talk about what is a medicine, okay?
Right.
In a modern day medicine, okay, if you take a atorvastatin or you take a blood pressure medication or you take a metformin, you take any of these things, what happens? You're taking a defined drug substance, a defined chemical entity that has a defined pharmacokinetic and pharmacodynamic profile with a defined pathway and a defined receptor engagement or target engagement. You know when you should take it, you know when you should not take it, you know who is contraindicated, you know all these things about modern day medicines, okay?
Right.
And yet, when we talk about exercise, the CDC recommendation is 150 minutes a week. Maybe you should also add resistance training. That is nothing at all in the way that we prescribe in modern day medicine.
Right. The specificity there is really missing.
Exactly. And so I think that where basic scientists like I have focused now is if we really want to bring home and bring to reality this idea of exercise as medicine, we can't just accept the fact that it has all of these benefits when you do it. What we have to do is define physical activity at the resolution that we define modern medicines. What is a molecule?
And now earlier in our conversation, you made an allusion to the fact that there's even disagreement about what constitutes physical activity. So where are we in that debate?
There's still disagreement, but I can tell you that, for example, from our work, I can define for you whether or not you've done sprint exercise by how much lac Phi you have. Okay? And so now we're starting to define in a much more nuanced, in a much more chemical, and a much more molecular way what different types of activity are. I can tell you that, for example, sprinting at a molecular and chemical level is different than walking around the block. Because when you walk around the block, your lac Phi levels do not change. And that's the first time that we've actually been able to define very clearly what the difference is between those two different types of physical activity. And I think as we start to understand more of the molecules of exercise, as we start to understand more molecules that, for example, are specifically induced by resistance training, that are not induced by endurance training, we'll be able to start to dissect out what exercise actually is and to be able to define in the same way that we define modern medicines.
Yeah, so this is a chance for me to ask you about metformin. So metformin is a diabetes drug. We've been using it for a couple of decades or longer. But recently, we've noticed people are starting to take metformin for things like life extension or to lose weight where they're not really obese, they don't have diabetes. Where does metformin fit into your world? It's a small molecule. Is it totally separate from all these issues, or is it intricately enmeshed?
So you would, from first principles, think, well, we discovered lac Phi in the context of exercise. You're talking about something totally different, a diabetes drug, metformin. These things should be totally unrelated. But actually what we found, and that was just reported this year, was that both exercise and metformin stimulate this lac Phi pathway. Okay.
Oh.
So in people that are taking metformin, metformin actually in people is a stronger inducer of lac Phi than sprint exercises. Okay. And that's sort of a very unexpected connection between two very, very different things. And we can show, at least in the mouse models, that the reason that you get weight loss on metformin is because of metformin's ability to increase lac Phi. And so I think that also highlights sort of the advantage of trying to understand these things from a chemical and molecular perspective, which is that we have now said, actually, these two things you think are very different. Sprinting and this anti-diabetic drug.
Unbelievable.
These are actually intimately connected. They converge on the same molecular and chemical pathways.
The
And so
other
as
thing
we
that
go
I
through-
love,
yeah.
that is a fantastic story. And the other thing that I love is we've been using metformin without knowing this for 20 years. And so it shows that vigilance and kind of scientific curiosity is absolutely critical, because now we can like get a mechanism of action for metformin, even though we've been using it successfully for 20 or 30 years. Okay, so let's go to the
Absolutely.
big, yes. Let's go to the big question. What is the prospects for an exercise pill? So just to review, you said, first of all, we need to define exercise. And you talked a little bit about, okay, we're starting to have some definitions that might be agreeable. You also said that it's not just about losing weight, because we also have to build up lean body mass. So what are the prospects, and what would one of these pills look like? And is it even worth pursuing, or should we just tell people to suck it up and get out there onto the weight training machines?
This whole idea of exercise in the pill has been around for a very, very long time. And I think, in the popular press, it's obviously oversold. But I think it gives basic scientists sort of an aspirational idea of what we should be thinking about doing, right? And it comes back to this idea of exercise as medicine. If we really want to make exercise as medicine a reality, what we ought to be able to do is understand the pathways of exercise well enough that we could develop a therapeutic that hijacks exercise pathways so that we can get some of the benefits. For example, especially in older individuals who can't exercise with as high intensity or as hard as they would need to get certain benefits, it could be very beneficial to have such a molecule exercise in a pill. And so, but I think also as basic scientists, we need to be very careful about how we're selling this to the public, which is to say that where are we in this? Okay, and it comes back to the very beginning of our conversation. Where we are is where the GLP-1 medicines were in the 1980s. We're in the fundamental basement here of trying to understand the science, okay? And when we talk about exercise as a pill, or exercise in a pill, or exercise in medicine, what we have to appreciate is that what we're really promising is maybe something that's going to come decades down the road built on this fundamental understanding. So I believe that we'll be able to get there, absolutely. But it's going to be on a much longer time horizon than people would like to have.
It also, I mean, we're not ready to start designing the pill, but it occurs to me that we have multiple goals here in terms of losing fat and gaining muscle, and those might be two separate. It might be a pill that has two different compounds in it. I mean, as long as we're speculating, right?
That's exactly right. As we start to think about exercise and the benefits of exercise, it may be that different pathways and different molecules are mediating different effects. Some that lack is mediating the effect on your appetite, that there's a different molecule mediating the effect to build strong bones and connective tissue. There's a different molecule that's mediating the antidepressive effects of physical activity, okay? And so as we start to think about that and uncover that, we may be able to, that's what we need to understand now in order to get to where you're talking about in the future.
Not to mention that profound sense of loss of anxiety and kind of complacency that you get after very vigorous exercise, which is, they call it the runner's high or whatever. And that may or may not involve lac-Phe, but you were talking about endocannabinoids and things. Right. So now I'm thinking about there's at least 3 molecules in there for the fat, for the muscle, and for the sense of well-being that you need to get from the exercise pill.
Exactly. Absolutely.
Okay. Thanks to Jonathan Long. That was the future of exercise. Thanks for tuning into this episode. With over 250 episodes in our archive, you have instant access to a wide range of discussions on the future of everything. Please remember to hit follow in the app that you're listening in now. This will guarantee that you never miss out on an episode and that you're fully aware of the future of everything. You can connect with me on X or Twitter at RB Altman, and you can connect with Stanford Engineering at Stanford ENG.